So back in 2011, my colleague Bob Howard asked me a question. He said, is it true that natural gas is a bridge fuel to a sustainable green energy future? And I looked at him and I said, what are you asking me for? What do I know? I'm a rock mechanic. He says, well, I'd like to try to address that question in a scientific way. Why don't we pose a scientific hypothesis? The hypothesis is that producing natural gas and burning it and leaking it is better for climate than if you were using coal or oil. Well, how would you test that hypothesis? Is it true or is it not true? It's a good question. We didn't know the answer in 2011. No one knew the answer. We don't know the answer today. It's now almost 2014. But nobody had asked the question in the peer-reviewed literature. So we published in a pretty famous journal. And we did an analysis of the existing information, none of which was based on hard data. It was all based on opinion. The Environmental Protection Agency, EPA, picks up the phone, calls Exxon, says, how much methane do you think leaks during flowback? Exxon says, well, we'll get together a committee at API and we'll address that and get back to you. And after some period of time, the API committee reports back to the EPA and we say, 1,000 gigograms per minute. And EPA says, okay. And then they say, well, how much is leaking from the pneumatic valves on the pads? We'll get back to you on that. So they discuss it at API, and they come back and tell EPA, it's this much. And EPA says, okay. That's the way the world worked. Nobody had ever gone out and actually measured how much methane was leaking at the wells, at the wellheads, during fracking, during compression, during gathering, from all the fittings and valves and pipes and transmission lines, storage units, distribution lines. Nobody had ever measured it. But we'd already established national policy of all the above. Drill, baby, drill. Somebody had already said it and believed natural gas is a bridge fuel to a sustainable green energy future because it's cleaner than coal or oil. So based on opinion, but not measurements, we wrote our paper. We took everybody's opinions, API, ANGA, DOE, EPA, every place we can find opinions. We put all the opinions together and we published this chart. So I got to explain the chart. The horizontal axis compares shale gas, conventional gas, coal, and diesel. And the vertical axis compares their effect on global warming. Don't worry about the units. This is the effect on global warming. The higher this number, the more effect, the higher the heating. There are three colors in each of those bars. The black color is how much carbon dioxide is emitted when you burn it. The blue color is how much carbon dioxide is emitted when you mine it. And the pink color is how much methane is emitted, converted into carbon dioxide equivalents using the global warming potential. Remember, you can convert methane into carbon dioxide because we know how much more potent methane is than carbon dioxide. So you multiply the amount of methane by 84, and that's the same effect that you would get if you had put out 84 pounds of carbon dioxide. And so since we didn't have data, we only had opinions. The low opinion was here, and the high opinion was here. Scientists do that. They don't like to answer with discrete numbers. There's never a number for an answer. There's always a number with a range of error associated with it. What's the reliability of that number? We talk about the probability density function, the bell-shaped curve, standard deviations, confidence limits. We didn't have data. We only had information. And the information was guesses. So we did the same thing for conventional gas. We did the same thing for coal, whereas here we had a lot of data. And here we had a lot of data. So what did we find out? Well, basic chemistry says when you burn methane, you get much less carbon dioxide than you get when you burn oil or coal. Everybody knows that. Hence, people think, because they're ignoring methane not being burned, that as long as you burn all the methane, you get less carbon dioxide than you do if you burn coal or oil. Therefore, if we substitute methane for coal or oil, we'll be better off for climate. And that's stupid, sloppy thinking, because it ignores the methane that doesn't get burned. When we take into account the methane that doesn't get burned, we find this. Our lowest estimate, based on other people's opinions, is that shale gas is dirtier than everything. It's dirtier than coal, dirtier than oil. Therefore, it's not a bridge fuel. It's a gangplank. Okay, well, that paper came out in 2011. We got blasted. Anybody from EID here? ANGA? API? You're kidding. Come on, be brave. Where are you?
I'm from the industry.
Good. Okay, so we got blasted by people in the industry and academia because we asked the question. And we dared offer an opinion. Although our paper was very clear. We said that this analysis is not based on measurements. It's based on opinions. Not ours, others. We collected all the opinions and got those numbers. In the paper we said, and we don't know what the right answer is. It could be this, it could be this, it could be in between, it might be lower. The only way we're going to find out is to measure. And so we implored whoever read our paper to get involved and go out and make measurements. And that started to happen. So now I'm going to show you what people are measuring. Industry talks about three streams when they talk about a fossil fuel: upstream, midstream, downstream. For gas, upstream means at the well pad. Midstream means from the well pad to the time it gets to a pipeline. Downstream means from a pipeline to the end use. So you can make measurements upstream, midstream, downstream, or mix. And I'm going to report on what the literature, the peer-reviewed literature, has discovered and written in the last 2 years since our paper. We asked the question, now we're getting the answers. So a paper in Nature by scientists from the National Oceanic and Atmospheric Administration and a bunch of academics went to the Uinta Basin in Utah, northeastern corner of Utah, where there's gas and oil production, has been for many years. And they determined that upstream and midstream, that is, including well pads, gathering lines, separators, condensate tanks, and compressor stations, but not transmission lines or distribution lines, up to 9% of the gas is being emitted without being burned. They went to the Denver-Julesburg Basin, north of Denver in Colorado, Weld County and surrounding counties. Again, upstream and midstream, this does not include transmission lines or distribution lines, between 2.3 and 7% leakage. We had predicted anywhere between that number and that number for all upstream, midstream, downstream, including all the pipelines. More recently, people are going into our major cities and our minor cities, recognizing that many people heat their homes with natural gas. Many industries use natural gas for industrial heating and industrial processes, so we have lots of pipelines under our cities. And like a lot of our infrastructure, these pipelines are getting old. Many of them are made of cast iron, or worse. And the joints in these cast iron pipes are failing and leaking. So I know you don't recognize this, but this is a map of Boston. This is downtown Boston. Here's Boston Harbor. Constitution sitting over here. The colors mean the following things. So scientists at Duke and Boston University drove up and down 700 miles of streets in Boston with a device that instantaneously measures the concentration of methane in the atmosphere and instantaneously determines by isotopic signature whether it's thermogenic or biogenic and whether it has mercaptan in it. And if it has mercaptan, you know what mercaptan is? It's the stuff that makes it stink. If it has mercaptan in it, it's leaking from a distribution line. Everything that's red is normal. Remember I told you we're breathing about 2 parts per million methane? So that's the normal background level. Anything that's gold is higher. And you can see places in downtown Boston where the methane concentration is 15 times higher than background. Okay? Over 2,000 leaks they found, 2,000 significant leaks. And just today there was an announcement by Senator Markey that he's going to introduce legislation that will change the ground rules for public utilities. You ready for this? All that methane that's leaking out of those pipes, who pays for it? The ratepayers. Because companies are allowed to pass on the cost of lost and unaccounted for gas. In other words, the companies know how much gas they're putting into the pipelines, and they know how much they're getting paid for. Therefore, they know how much they're not being paid for. Therefore, they know how much they're losing, and therefore, they can increase their rate so they can get their guaranteed 7% rate of return. So over the last 10 years, ratepayers in Massachusetts have paid $1 billion for gas they never got. Somebody should make a law. New York City, about a 3% leakage rate overall. And this is the shocking part. 70% of the cast iron pipe, Con Ed is the gas utility in New York City, is over 100 years old. One of the very first projects I worked on at Cornell back in the early 80s was for Con Ed, trying to figure out what they could do about all these leaky cast iron pipes. Anybody recognize the city? This is the same team, people from Duke and Boston University. They're going to a lot of the major cities and doing the same kind of measurements. This is Washington, D.C. 5,893 pipeline leaks on 1,500 road miles in Washington, D.C., including leak rates is, again, let's see, that's 27 times background. 13 times background, close to the Capitol building. Some of these leaks are what are called Category 1 leaks. These are typically at major intersections where there are manhole covers, and the manhole covers are covering up the gas pipelines, and they found, I think, 26 or 27 intersections where the methane concentration under the manhole was 80% methane or more. In other words, explosive. And they're having situations where they're exploding manhole covers. They should be fixed. Downtown Los Angeles has an active oil and gas field. Downtown Los Angeles, within the city limits, there's an active oil and gas field. So same techniques. This is done by NOAA. This is the natural background level, about 2 parts per million. And here are the spikes that they're noticing around that gas and oil field. And so this is from the latest paper, looking at the Los Angeles basin. Up to 17% of the natural gas produced in the region is leaking. So I think what we predicted, based on guesses, is conservative compared to what's actually being measured, unfortunately. I said there's a triple whammy with methane. So when you burn it, you get carbon dioxide. That's a greenhouse gas. So increasing our production of methane is increasing carbon dioxide in the atmosphere. And that's the wrong way, but it's also getting unburned methane in the atmosphere, and I assure you that's bad. But you've probably seen pictures like this. This is, where's Houston? Washington. Okay. So periodically processing plants have to blow down and burn off. And they're not burning off pure methane.
That was a hiccup in the new equipment.
Yeah. Well, it hasn't just happened once. And when it happens, then you get black carbon. So. Okay. So what does this all mean? Try to sum it all up here now. I came here tonight to talk to you about leaking wells, and I said there were going to be 2 aspects of leaking wells that were going to be important to you. One would be local. Can a leaking gas well affect my drinking water well? And the answer is yes, it could. Will it inevitably? No. What's the probability? We're getting close to being able to answer that question. We have a lot more data from which to extract information than we had 5 years ago. I also said we look at the other end of the spectrum, which is when a well leaks, puts methane into the atmosphere. And methane is a greenhouse gas, and it's very potent. So now I want to explain to you this is the last chart. Stay with me, last one. This also appeared in the Journal of Science. Came out last year, so it's now a year old. Done by a very large number of the very best climate scientists around the world, headed by Dr. Drew Shindell at NASA. And it's the best picture we had a year ago at our climate future and past from the point of view of global warming. So once again, I'll explain everything that's in the chart, and then we'll decide what information it's transmitting to us. Horizontal axis is year. Here's 1900. Here's 2010. This paper appeared in 2012 based on analysis that was done at the end of 2010. Here's 2070. This is a measure of global warming. You've all heard about the 2 degrees centigrade limit. The fact that we've had about 0.8 of a degree centigrade warming. This is actual measurements, the squiggly line. You shouldn't expect that the Earth is going to warm uniformly with a beautiful smooth curve. There are ups and downs. Sometimes it cools in a year, sometimes it warms in a year. Sometimes there are whole periods when it cools off, and then